On the 21st of August, 1940, as German bombers darkened the skies over southern England with monotonous regularity, a peculiar gathering took place inside a nondescript laboratory at Birmingham University. Professor John Randall stood before a crude apparatus that resembled nothing so much as a plumber's failed experiment, a copper cylinder riddled with holes, connected by seemingly haphazard wiring to equipment salvaged from various corners of the physics department. His colleague, Harry Booth, adjusted his spectacles nervously as they prepared to test what many of their peers had dismissed as theoretical nonsense: a cavity magnetron capable of generating microwave radiation at unprecedented power levels. The timing could not have been more critical. Britain stood alone against Nazi Germany, its cities suffering nightly bombardments during what would become known as the Blitz. The Royal Air Force's chain home radar stations along the coast provided early warning of incoming raids, but these massive installations, with their 350-foot towers and equipment housed in buildings the size of warehouses, represented the limit of British radar technology. Ground-based systems could detect enemy aircraft approaching across the channel, yet British fighter pilots still hunted their quarry largely by once airborne, guided only by radio instructions from controllers squinting at cathode ray tubes far below. The fundamental problem vexing British scientists and military planners alike was one of physics and practicality intertwined. Radar worked by transmitting radio waves and detecting their reflections from distant objects, but the wavelength determined everything. The existing radar systems operated on wavelengths of several meters, requiring enormous antennas and transmitters that consumed enough power to light a small town. To miniaturize radar sufficiently for installation in fighter aircraft, engineers needed to shift to much shorter wavelengths, ideally 10 centimeters or less, which would allow proportionally smaller antennas while providing better resolution for tracking individual aircraft. But therein lay the cruel paradox that had stymied researchers across Europe and America. Generating powerful radio waves at such short wavelengths seemed to violate the fundamental limitations of vacuum tube technology. The conventional klystron tubes that American researchers favored could produce microwave frequencies, but only at power levels measured in milliwatts, barely enough to illuminate a flashlight bulb, much less send a detectable signal bouncing off an enemy bomber several miles away. What British radar desperately needed was a source capable of producing kilowatts of continuous microwave power in a package small enough to mount in the nose of a Beaufighter or Spitfire. Randall and Booth's cavity magnetron represented a radical departure from orthodox approaches. Rather than attempting to push conventional vacuum tube designs to their limits, the two physicists had essentially reinvented the device from first principles. Their design trapped electrons in a circular dance using powerful magnets, forcing the charged particles to spiral past a series of carefully dimensioned cavities machined into a copper block. When conditions aligned precisely, magnetic field strength, cavity dimensions, applied voltage, all balanced in delicate harmony, the electrons would excite resonant oscillations in the cavities, generating microwave radiation that emerged from a small antenna probe. The concept itself traced back to pre-war theoretical work, but transforming elegant mathematical descriptions into functioning hardware required intuition bordering on art. According to reports later published in the Proceedings of the Royal Society, the precise dimensions of those copper cavities had been determined through painstaking experimentation, each test requiring hours of calculation and machining, followed by moments of truth when power flowed and instruments either registered success or confirmed another failure. The morning of the 21st of February, 1940, had begun unremarkably enough for Booth, a young physicist barely 3 years removed from his doctorate. He arrived at the Nuffield laboratory to find Randall already hunched over their workbench, manipulating a small copper cylinder with the concentration of a jeweler examining a precious stone. The device measured roughly 4 inches in diameter, small enough to cradle into hands. Yet its creation had consumed months of their lives and represented Britain's best hope for transforming radar from a static defensive tool into an offensive weapon that pilots could carry into battle. The previous attempts at microwave generation had followed predictable patterns, each iteration revealing new obstacles. American engineers at Bell Laboratories had achieved modest success with klystron tubes, devices that bunched electrons into discrete packets and accelerated them through resonant cavities. The Stanford physicists Russell and Sigurd Varian had pioneered this approach in 1937, demonstrating the basic principles of velocity modulation. But their design, while elegant in conception, suffered from inherent limitations. The tight electron bunching required for efficient microwave generation demanded extraordinary precision in manufacturing, and even then, power output remained disappointingly low. British researchers had initially pursued similar paths, but the magnetron represented something fundamentally different. The concept originated with Albert Hull at General Electric's research laboratories in Schenectady, New York, who had explored magnetron principles as early as 1921. Hull's original device had been intended as a switching element rather than an oscillator, but subsequent researchers recognized that under certain conditions, magnetrons could generate radio frequency oscillations. The problem was controlling and maximizing this effect. What Randall and Booth accomplished in that cramped Birmingham laboratory was transform an interesting physics curiosity into a practical engineering marvel. Their cavity magnetron employed 8 cylindrical cavities machined with micrometer precision into a solid copper block. These cavities, each approximately 1 centimeter in diameter, surrounded a central cathode like the chambers of a revolver. When high voltage was applied and powerful permanent magnets created a perpendicular magnetic field, electrons emitted from the cathode found themselves unable to travel directly to the anode. Instead, the magnetic force bent their trajectories into circular paths. This forced circular motion created the conditions for a remarkable phenomenon. As electrons swept past the cavity openings, they interacted with the oscillating electromagnetic fields within those cavities. Electrons arriving at just the right phase would be accelerated, while those arriving at the opposite phase would be decelerated. This velocity modulation organized the initially random electron cloud into rotating spokes of charge density, spinning around the cathode at precisely the frequency determined by the cavity dimensions. The organized electron spokes then fed energy back into the cavities with tremendous efficiency, sustaining powerful oscillations. The mathematics describing this process filled pages with partial differential equations and boundary conditions. But Randall and Booth had supplemented theoretical calculations with practical experimentation. According to documentation preserved in the archives of the Institution of Engineering and Technology, they tested dozens of cavity configurations, varying dimensions by fractions of a millimeter, searching for the magical combination that would produce maximum power output at the desired 10-centimeter wavelength. On that February morning, they prepared to test their latest iteration. Both connected the high-voltage power supply while Randall checked the magnetic field strength. With a Gauss-meter, the room's atmosphere carried the ozone tank characteristic of high-voltage electrical equipment, mixed with the metallic scent of hot copper. At precisely 10:15, Randall nodded, and Booth closed the main power switch. For 3 seconds, nothing seemed to happen. Then the neon indicator lamp connected to their detection circuit blazed with sudden incandescence. The ammeter needle swung wildly across its scale before settling at a reading that made both men catch their breath. The magnetron was producing not milliwatts, but kilowatts, roughly 100 times more power than any previous microwave source had achieved. In that moment, airborne radar transformed from theoretical possibility to engineering inevitability. On the 29th of September, 1940, a wooden crate containing Britain's most closely guarded military secrets sat in the hold of a flying boat preparing to depart from Poole Harbor. Inside that crate, packed with extraordinary care among official documents, blueprints, and technical specifications, rested a single-cavity magnetron, the 12th such device successfully produced by the team at Birmingham University. The magnetron was accompanied by diagrams detailing its construction, theoretical analyses of its operation, and performance data that American scientists would initially dismiss as impossible. The man responsible for this unprecedented transfer of technology sat in the passenger cabin, reviewing documents that represented the culmination of months of intense debate within British scientific and military circles. Sir Henry Tizard, a distinguished chemist and rector of Imperial College London, led what would become known as the Tizard Mission, a delegation of British scientists tasked with sharing Britain's radar research with American counterparts in hopes of accelerating development of improved systems that British factories, strained by wartime demands, could not produce quickly enough. The decision to reveal the magnetron's secrets to the Americans had not come easily. Winston Churchill's government understood that this single device represented an enormous technological advantage. German radar research had followed different paths, and intelligence reports suggested that Nazi scientists had not yet achieved comparable microwave power outputs. Sharing the magnetron with America meant potentially shortening Britain's lead in this critical technology. Yet pragmatism demanded such risks. Britain's industrial capacity was stretched to breaking point. Aircraft factories worked triple shifts to replace fighters lost in daily combat. Shipyards struggled to construct vessels faster than German U-boats could sink them. The precision manufacturing required to produce cavity magnetrons in quantity, the careful machining of copper cavities to tolerances measured in thousandths of an inch, the sourcing of powerful rare earth magnets, the development of specialized vacuum pumps exceeded what British industry could readily support, while simultaneously maintaining production of conventional weapons. According to accounts later published in The Invention That Changed the World, a comprehensive history of radar development by Robert Buderi, the magnetron initially encountered considerable doubt among American researchers when members of the TIZARD mission first approached their counterparts at the Radiation Laboratory, being established at the Massachusetts Institute of Technology. American physicists received the British claims about kilowatt-level microwave generation with polite but evident disbelief. The numbers simply seemed too good to be true. American researchers had been laboring for years to coax adequate performance from klystron tubes, accepting fundamental limitations as the unavoidable price of working at microwave frequencies. The demonstration that shattered this skepticism took place in early October 1940 in a laboratory at Bell Telephone Laboratories in New Jersey. British scientist Eddie Bowen, a member of TIZARD's delegation, supervised as American technicians connected the Birmingham magnetron to a simple circuit designed to measure power output. The test required only minutes to set up, but those minutes felt eternal to the assembled observers. British scientists anxious that their device might fail to perform after its transatlantic journey. American researchers anticipating confirmation of their suspicions about exaggerated British claims. When power flowed through the magnetron, the measuring instruments registered readings that left the American scientists stunned. The device was producing approximately 10 kilowatts of pulse microwave power at a wavelength of approximately 10 centimeters, exactly as the British had claimed, but so far beyond contemporary American achievements that several observers initially suspected measurement error. Subsequent tests confirmed the readings were accurate. The British had indeed achieved what American physics had deemed impossible. On the 11th of November, 1940, barely 6 weeks after the TIZARD mission's arrival in Washington, a hastily assembled team of American physicists gathered on the 4th floor of Building 20 at the Massachusetts Institute of Technology. The building itself was a temporary structure, erected quickly using wood framing to house wartime research projects that couldn't wait for proper facilities. Its floors creaked under the weight of equipment being hauled up narrow stairwells, and its walls provided minimal insulation against the November chill. But it would serve as the unlikely birthplace of American microwave radar. The organization established in that ramshackle building carried an intentionally misleading name, the Radiation Laboratory. The radiation in question had nothing to do with nuclear physics, but the vague designation served its purpose, discouraging unwanted curiosity about the facility's actual mission. In reality, the Radiation Laboratory existed for one purpose: to transform the British cavity magnetron from laboratory curiosity into mass-produced reality, then design the myriad systems required to exploit its revolutionary capabilities. Lee Dubridge, recruited from the University of Rochester to serve as the laboratory's director, faced challenges that would have daunted less determined men. His mandate was to accomplish in months what would normally require years: establish a complete research and development organization capable of designing operational radar systems from scratch, develop manufacturing processes for the intricate magnetron, coordinate with military services whose requirements often contradicted each other, and somehow maintain security despite employing hundreds of scientists and technicians who would need access to classified information. The magnetron itself presented immediate manufacturing challenges. The device that Randall and Boot had painstakingly constructed in Birmingham represented proof of concept, but its production had involved countless hours of skilled labor filing, measuring, adjusting, testing by two exceptionally talented physicists who understood intimately how every dimension affected performance. translating their artisanal approach into industrial mass production would require developing entirely new manufacturing techniques. By early 1941, the first American-manufactured magnetrons began emerging from production lines. These units incorporated subtle improvements over the original British design: better heat dissipation, more reliable vacuum seals, standardized mounting dimensions while maintaining the fundamental principles that made the device work. Production rates climbed from dozens per month to hundreds, then thousands, as multiple manufacturers tooled up and learned the demanding processes required. Simultaneously, the Radiation Laboratory's technical divisions attacked the equally daunting challenge of designing complete radar systems around the magnetron. A radar required far more than just a microwave source. Engineers needed to develop high-speed switching circuits capable of toggling the magnetron between transmitting and receiving modes thousands of times per second. Design antennas that could focus the 10-centimeter microwaves into narrow beams. Create sensitive receivers that could detect the faint echoes returning from distant targets. And devise display systems that would present this information to operators in readily interpretable form. The display problem alone consumed months of development effort. Early radar systems had used simple scope displays. Cathode ray tubes show and receive signal strength as vertical deflections on a horizontal time base. These displays worked adequately for ground stations where operators had time to interpret subtle patterns, but pilots in combat needed something more intuitive. The solution emerged as the Plan Position Indicator, or PPI display, a circular screen that showed targets as bright spots at their actual angular positions and ranges relative to the aircraft, creating a map-like presentation that pilots could grasp instantly. Edward Bowles, a mid-professor serving as consultant to the Secretary of War, described the atmosphere at the Radiation Laboratory during this period as resembling controlled chaos punctuated by moments of breakthrough. Teams worked around the clock, sleeping on cots in offices between shifts, driven by acute awareness that every day's delay meant more Allied ships torpedoed by U-boats, more bombers failing to find their targets, more fighters shot down because they couldn't locate enemy aircraft in darkness or clouds. On the 17th of March, 1941, Flight Lieutenant John Cunningham guided his Bristol Bullfighter through absolute darkness, 3 miles above the English countryside. His radar operator, Sergeant Jimmy Rawnsley, hunched over the new American-made SCR-540 airborne intercept radar, watching the cathode ray tube intently as greenish traces danced across its face. Somewhere ahead in that darkness flew a German bomber Rawnsley had picked up its signature minutes earlier as a faint blip. At the edge of their detection range, the transformation of microwave radar from laboratory achievement to operational weapon system had required solving a cascade of interconnected problems, each solution creating new challenges. Installing a complete radar system in a fighter aircraft demanded extraordinary miniaturization, while maintaining the ruggedness needed to survive combat conditions. The magnetron itself occupied relatively little space, a cylinder roughly the size of a grapefruit, but the complete system included high-voltage power supplies, cooling systems, transmit-receive switches, receiver circuits, and a display console. British engineers working with the Telecommunications Research Establishment at Malvern had pioneered the first airborne intercept radars even before the cavity magnetron's invention. These earlier systems, operating at wavelengths of 1 1/2 meters, had achieved operational success despite their limitations. RAF night fighter crews using this equipment had demonstrated that radar-equipped aircraft could locate and intercept enemy bombers in complete darkness, a capability that transformed the strategic balance of the night bombing campaign. But the longer wavelength systems suffered from fundamental constraints. Their large antennas required by the physics of meter wave propagation protruded awkwardly from aircraft noses, creating significant aerodynamic drag. More critically, the resolution of radar systems improved proportionally with decreasing wavelength. The meter wave radars could detect a bomber at ranges of several miles, but they provided only crude directional information. Pilots often found themselves circling frustratingly close to their quarry, unable to achieve the precise positioning required for a visual acquisition and attack. The 10-centimeter microwave radar systems enabled by the cavity magnetron transformed this equation fundamentally. The shorter wavelength permitted antennas measuring mere feet across rather than dozens of feet, housed entirely within streamlined nose fairings that added minimal drag. More importantly, the improved resolution allowed radar operators to track targets with precision measured in degrees, rather than tens of degrees. This improvement meant the difference between knowing an enemy bomber was somewhere ahead and knowing its exact position relative to the fighter Cunningham's success on that March night demonstrated the new system's capabilities dramatically. Following Rawnsley's directions, he maneuvered the Beaufighter into position behind and slightly below the German bomber, approaching the visual range without the enemy crew's awareness. The bomber, a Heinkel 111, according to subsequent confirmation, appeared suddenly in Cunningham's gun sight as a dark silhouette against the slightly lighter sky. His cannon fire struck with devastating effect, and the bomber fell in flames. It was the first of many such victories that would establish Cunningham as the leading night fighter ace. According to documentation later published in Instruments of Darkness, Alfred Price's authoritative history of electronic warfare, the introduction of centimetric radar to RAF night fighters initiated a period of dramatic success. Against German night bombers, Luftwaffe crews, who had previously enjoyed relative impunity in darkness, found themselves increasingly vulnerable to interception regardless of weather conditions or moonlight. The psychological impact on German bomber crews proved as significant as the actual losses. The knowledge that British fighters could find them anywhere, anytime, in any conditions. American aircraft soon received similar equipment. The Radiation Laboratory had developed the SCR-720 series, specifically for installation in American night fighters, optimizing the system for the P-61 Black Widow and later the F-6F Hellcat. These radars incorporated refinements learned from RAF operational experience, improved skin patterns, better ground clutter rejection, enhanced reliability under the severe vibration and temperature extremes encountered in combat aircraft. The Pacific Theater presented unique challenges that tested microwave radar capabilities. The vast distances of Pacific operations meant fighters often operated far from friendly territory, where equipment failures could prove fatal. The tropical climate subjected electronics to temperature extremes, humidity levels that promoted corrosion, and fungal growth on organic materials used in circuit insulation. Engineers responded with tropical packaging techniques, hermetic sealing of sensitive components, fungus-resistant varnishes, improved ventilation systems that dramatically improved reliability. Lieutenant Commander Willis Wenz, flying an F-6F Hellcat equipped with the latest radar from the carrier USS Hornet, described the experience of night interceptions in his combat reports. The radar presentation was clear enough to vector directly to the target, with range and bearing continuously updated. I made several successful intercepts of Japanese bombers that would have been impossible to locate visually. The equipment performed flawlessly despite the harsh conditions. On the 9th of May, 1942, a consolidated B-24 Liberator bomber equipped with the new ASV Mark II radar lifted off from an airfield in Northern Ireland, beginning a patrol over the black waters of the North Atlantic. In the aircraft's nose, a radar operator monitored his screen, searching for the distinctive signature that would indicate a surface submarine. The Battle of the Atlantic had reached its critical phase, with German U-boats sinking Allied merchant ships faster than shipyards could replace them. If the current loss rates continued, Britain would be strangled by maritime blockade regardless of victories on other fronts. Submarines represented an asymmetric threat that had nearly won the First World War for Germany, and threatened to do so again in the Second. A U-boat could patrol for weeks, surfacing only to recharge batteries and transit at higher speeds between patrol areas. Submerged, submarines were nearly invisible to surface ships, detectable only by active sonar at relatively short ranges. The vast expanse of the Atlantic provided hiding space for entire fleets, and convoy routing could only reduce, never eliminate the probability of deadly encounters. The introduction of airborne radar to maritime patrol aircraft transformed anti-submarine warfare profoundly. Aircraft equipped with meter-wavelength ASV radar could detect surface submarines at ranges of several miles, allowing patrol planes to locate and attack U-boats that previously could surface with relative impunity in remote ocean areas. But the longer wavelength systems suffered from sea clutter radar returns from ocean waves that obscured submarine signatures and provided insufficient precision for effective attack runs. Centimetric radar solved these problems with dramatic effectiveness. The shorter wavelength dramatically reduced sea clutter, allowing detection of submarine conning towers even in rough seas. The improved resolution permitted radar operators to track submarines precisely enough to vector the aircraft directly overhead for depth charge or bomb attacks. Most critically, the 10-centimeter radar provided these capabilities using antennas small enough to be installed in aerodynamically clean nose mountings or wing pods, avoiding the performance penalties of the unwieldy antenna arrays required by longer wavelength systems. Captain Frederick Walker, commanding the 2nd Support Group of anti-submarine vessels, later wrote in his operational reports about the transformation wrought by aircraft equipped with centimetric radar. Previously, submarines could surface at night with reasonable confidence of remaining undetected between air patrols. The new radar has made night surfacing suicidal in areas where aircraft are operating. We have observed a marked change in U-boat tactics as they adapt to this new threat. The German submarine command initially failed to recognize what had changed. Admiral Karl Denitz's U-boat headquarters received increasingly desperate reports from submarine commanders describing surprise aircraft attacks in darkness and poor visibility, attacks that occurred without the warning that radar warning receivers should have provided. The existing German radar detectors monitored frequencies corresponding to the meter wavelength systems previously used by Allied aircraft. They provided no warning of the centimetric transmissions from the new microwave radars. According to post-war analyses documented in the U-boat war by Clay Blair, the period from mid-1942 through mid-1943 witnessed a steady increase in U-boat losses to aircraft equipped with centimetric radar. German submariners, unable to surface safely to recharge batteries or transit between patrol areas, found their operational effectiveness severely compromised. Submarines forced to remain submerged consumed battery power rapidly, reducing speed and range to the point where effective patrol operations became impossible. The Germans eventually captured examples of Allied centimetric radar equipment from downed aircraft and captured vessels and rushed to develop countermeasures. But the Allied lead in microwave technology, established by the cavity magnetron's early development, proved insurmountable. By the time German electronics firms developed radar warning receivers capable of detecting 10-centimeter transmissions, Allied forces had already shifted to 3-centimeter systems, using improved magnetrons, and the cycle began anew. The impact extended beyond simple detection. The Radiation Laboratory developed the H-2S radar specifically for bomber navigation and target identification. This system employed a downward-looking antenna that created planned position indicator displays showing the terrain beneath the aircraft. H-2S-equipped bombers could navigate accurately in any weather, identify targets through clouds, and conduct precision attacks without visual reference to the ground. When installed in maritime patrol aircraft, H-2S provided unprecedented capability for locating ships and submarines even in the worst weather conditions. On the 18th of December, 1943, a formation of Boeing B-17 Flying Fortresses thundered through dense overcast above northern Germany, their crews unable to see the ground 5 miles below. In the lead bomber, a radar navigator studied his H-2S display, watching as the electronic map of Bremen's industrial district scrolled across the circular screen. The city's distinctive features the Weser River's meandering course, the dense clustering of factories along its banks, the regular grid of streets in the city center appeared as light and dark patterns on the greenish display, clear enough for precise navigation despite the solid cloud cover extending from ground level to 20,000 feet. The strategic bombing campaign against Germany had encountered a frustrating paradox. Daylight raids achieved accuracy, but suffered terrible losses to German fighters and anti-aircraft defenses. Night raids reduced losses, but achieved accuracy so poor that many bombs fell on empty fields miles from their intended targets. The Reichsbomber Command had analyzed thousands of reconnaissance photographs and concluded that even on clear nights, fewer than 1/3 of bombs fell within 5 miles of their designated aim points. In overcast conditions, accuracy deteriorated further to the point where bombing became little more than random terrorism against the German civilian population. Radar solved this problem with revolutionary effectiveness, transforming strategic bombing from an art dependent on visibility and crew skill into a science of electronic precision. The development of the H-2S radar, the designation stemmed from Home Sweet Home, a sardonic reference to its original intended purpose as a navigation aid for bombers returning to base, provided bombers with the electronic equivalent of vision through clouds, darkness, and smoke. The system's design exploited the cavity magnetron's capabilities brilliantly. A spinning antenna in the aircraft's belly scanned the terrain below, while the transmitter pulsed thousands of times per second. Returns from the ground were displayed on a planned position indicator synchronized with the antenna rotation, creating a map that updated continuously as the aircraft flew. Different terrain features reflected radar waves differently. Water appeared dark, urban areas bright, with intermediate shades for forests, farmland, and open country. According to technical documentation preserved in the archives of the Imperial War Museum, the H-2S Mark III version, employing a 3-centimeter magnetron developed at the Radiation Laboratory, provided resolution sufficient to identify individual large buildings in city centers. Radar navigators could pick out specific factories, rail yards, or docks from the electronic terrain, then guide their bombers to precise release points regardless of visual conditions. The operational impact proved transformative. Raid after raid that would previously have been canceled due to cloud cover now proceeded with confidence. German industrial production, which had continued relatively unscathed during periods of extended overcast, suddenly became vulnerable to attack in all weather conditions. The psychological impact on German civilians proved equally significant. The wailing of air raid sirens now preceded bombing runs regardless of cloud cover, eliminating the sense of safety that overcast skies had previously provided. German scientists, analyzing wreckage from shot-down British bombers, quickly identified the H-2S radar and understood its implications. Hermann Goering, commanding the Luftwaffe, reportedly flew into a rage upon learning that British bombers possessed terrain mapping radar. While German industry had failed to produce equivalent systems, he ordered crash programs to develop German countermeasures and indigenous radar mapping systems, but German electronics